Hi. In this section of the Math Olympiad course, we are going to look at problems on functions and their graphs. So a lot of problems that we will see, we'll be using graphs to simplify our problem solving. And let's get with the problems and we'll understand the ideas involved in this section. So we'll start with the first question. The first question is this. Let f of 0 x be defined as mod of x and f of 1x be defined as mod of f of 0x minus 1, whereas f of 2x is defined as mod of f of 1x minus 2. Now, the question is asking us to find the area of the closed region between the graph of f of 2x and the x-axis. So it's a fairly straightforward question, but you need to know how to transform the graphs here. So if I draw, for example, f of 0 of x, right? That is the mod x function. So the graph looks like this. Now, in order to draw the graph of f of 1 of x, this is f of 0x, I need to first transform this graph. So f of 1 of x will be displacing the f of 0 of x or mod x graph by 1 unit down. It's a downward transformation, and then there is a modulus. So if there is a modulus, what we have to do here is take all the negative parts of the graph and reflect it above the x-axis. About the x-axis, we are reflecting it. So this is the graph of f of 1 of x. The shaded part is getting reflected. The dotted part is getting reflected, and this is 1. So this becomes your f of 1 of x. Now, if I want to find out f of 2 of x, what we need to do is put this graph down by 2 units, right? First step is that, translate it down vertically by 2 units. So if you draw that here, I will get, so the point 1 here will come at minus 1 now, right? So it should be like this, and then it should be like this, right? This is the translated version of the graph, and now these intersection points will be at 3, minus 3 and 3, right? Now, that is not all. We have right now just found the graph of f of 1 of x minus 2. Then we have to do the modulus here, which will be again a reflection. So I will reflect it like this here. I will reflect it like this here. And I have made a mistake here in drawing. Like this and like this. And basically this portion of the graph will be removed, right? The negative portion is gone and you just have the top parts here. And this is 1 and this is obviously be 2. It will be basically minus 1 comma 2. The height is 2. And this is going to be 1 comma 2, right? So this becomes your graph of f of 2 of x, roughly. You can draw it yourself accurately. What we have to find is the area of the closed region between the graph of f of 2 of x and the x-axis. So basically this area, this weird type of figure, this whole area we need to find, right? So a simple way to do that would be to think of it mentally like a trapezium here, join it. So area of the trapezium minus area of this triangle, right? So if I label it, let's call it A, let's call this D, C, let's call this E, let's call this B. Required area is basically area of ADCB minus area of DCE, right? So area of the trapezium becomes half into sum of the parallel sides. This side is 6 units and this side is 2 units. So 2 plus 6 into distance between them, which is 2 units. This height is 2 units. Minus area of triangle is half into base into height. This is 2 units and height is 1 unit. So half into 2 into 1. So this becomes basically 8 minus 1, which is 7. So The question is fairly easy if you know how to transform the graphs. So when you do a f of x plus minus k to a graph, this plus minus k basically shifts it above or below, right? And then when you take a modulus, you are reflecting all the negative parts and making it positive, right? So that is how you handle this first question. Hope you have learned something about transformation of graphs from this. Let's move on. Let's go to the second one. Let f of x and g of x be defined on R, and the graph of f of x is symmetric with respect to the line x is equal to 1, whereas the graph of g of x is centrally symmetric with respect to the point, with respect to the point 1 comma minus 2. Now suppose f of x plus g of x is equal to 9 power x plus x cube plus 1. We have to find the value of f of 2 multiplied by g of 2. So they have given us f of x plus g of x. We have to find f of 2 multiplied by g of 2. And we have been given some information that the graph of f of x is symmetric with respect to the line f x is equal to 1, whereas the graph of g of x is symmetric with respect to the point 1 comma minus 2, right? So let's think about it. If the graph is symmetric about a line x is equal to 1, this basically that means that any point here there will be equally symmetric graph here, right? This is the f function, it is symmetric about the line. So that means if I want to find f of 2 is 1 unit to this side, so it will be equal to whatever is f of 0. F of 2 will be equal to f of 0 because f function is symmetric about x is equal to 1 line, right? I hope everyone understands this part. Let's also think about what it means to be centrally symmetric about a point 1 comma minus 2. So 1 comma minus 2 is this point, 1 comma minus 2, this is minus 2 level, and this is x is equal to 1, let's say. So if 1 comma minus 2 is this point and the graph is symmetric about the point, we will have something like this, right? Just like y is equal to x cube is symmetric about 0, 0. I'm taking that similarity and I'm saying that this function g of x is symmetric about this point. So anytime you go a little distance above it, right? So for example, if your x coordinate was 1 plus h, right? 1 plus h. And your x coordinate here was 1 minus h, right? The y value here would be g of 1 plus h would be minus 2 plus k, and here it would be minus 2 minus k. So what am I saying here? I'm saying that because of the symmetry, the way y is equal to x cube is symmetric, g of 1 plus h should be equal to minus 2 plus k, and g of 1 minus h should be equal to minus 2 minus k, right? Because as you go up, the amount you have gone up, you will go down equally on the other side, because this is the point of symmetry, right? So that implies that g of 1 plus h plus g of 1 minus h should be equal to, when you add these two, it will become minus 4. And if I put h is equal to 1 here, I will get g of 2 plus g of 0 should be equal to minus 4. So that is my second condition. This is my first condition, this is my second condition. These are the two conditions that you can derive from the symmetries that are explained in the problem. If f of x is symmetric about a line x is equal to 1, this happens. If g of x is symmetric about the point 1 comma minus 2, this should happen, right? So once we have this information, we'll be easily able to solve the question because they have given us f of x plus g of x. So I will just use that here. So from there, we can say that f of 0 plus g of 0 is equal to, when you put 0 here, you get 2, and f of 2 plus g of 2 is equal to 9 square 81 plus 8 plus 1, so 90, right? Okay. Now we also have these two conditions. We have to find the product of f of 2 and g of 2. So we can say that g of 0 is equal to minus 4 minus g of 2 using this condition. G of 0 is minus 4 minus g of 2, and we can now put this here. So we'll get f of 0 minus g of 2 minus 4 is equal to 2. So you're getting f of 0 minus g of 2 is equal to 6. And we can use this here, and we'll be able to say f of 0 is f of 2. So we get f of 2 minus g of 2 is 6, right? Understand which results we are using. We have used this result to get g of 0 as this, and then f of 0 plus g of 0 is 2, and instead of g of 0 I put this. So I got f of 0 minus g of 2 is equal to 6, and we also know that f of 2 is equal to f of 0. So now I got f of 2 minus g of 2 is 6. Now combining f of 2 plus g of 2 is equal to 90, and f of 2 minus g of 2 is equal to 6, we will be able to solve for f of 2 and g of 2. If you simply add, you will get f of 2 is equal to 48, and therefore g of 2 must be equal to 42, right? So the product of f of 2 and g of 2 is 48 times 42, which is 2016. I hope you have understood this problem. The main idea is to understand how to handle the symmetries. So if I draw the graph, you will get a sense of this inequality, this equality. This is an identity that is satisfied for the g function. If you can get this identity correctly, the problem is pretty straightforward, right? If you have not understood the question, please go back a few minutes in the video and try to work it out yourself. It is fairly easy. You should be able to understand it. Let's move on. The next question is this one. Suppose f of x is equal to root over x plus 2 plus k, and there exists a and b where a is less than b such that the range of f of x for x belonging to a and b is a and b, the enclosed interval a to b. We have to find the range of k. Find the range of k for this to be true, right? Now let's think about it. We have been given a function, and we have been told that there are two real numbers a and b such that the range of f of x for x belongs to a to b is itself a to b, right? So first of all, what is the domain of the function? The function is defined for x greater than or equal to minus 2. That is obvious because of this root, right? Then we can quickly see from the nature of the function, the root of x plus 2 is always increasing and k is a constant, right? So f of x is monotonically increasing function. Monotonically increasing, right? So basically, as x increases, f of x increases. So that means f of x range for x belongs to a to b should be between root over a plus 2 plus k to root over b plus 2 plus k, right? Because it's an increasing function, you can take the lower limit, that will be the lowest possible value of the function, and upper limit, and that will be the highest possible value of the function. Now, in the question, they are saying that the range of the function is actually same as a to b. So that means this must be equal to a and this must be equal to b, right? So if I say this equation, root of a plus 2 plus k is equal to a, and this equation root of b plus 2 plus k is equal to b. Basically what I'm saying are that a and b are two roots of root over x plus 2 plus k equal to x, right? That is what I am saying here. These two things must imply this. And if there are two roots of this, I can say root over x plus 2. I can make it a quadratic x minus k. And x plus 2 is equal to x square plus k square minus 2kx. And rewriting that quadratic a little bit, you will get x square minus 2k plus 1x plus k square minus 2 equal to 0. This quadratic has two roots, a and b, right? If it has two roots, obviously we can put a condition on the discriminant. Discriminant must be greater than equal to 0. So if discriminant is greater than equal to 0, let's see what that implies. So del is greater than 0. That implies 2k plus 1 whole square minus 4 times k square minus 2 is greater than 0. If you solve this, you will realize that 4k square will get cancelled and it will be a linear expression. And from there, we can deduce that k is greater than minus 9 by 4. You can solve that yourself. It's fairly straightforward. We get that k is greater than minus 9 by 4. Also, because this equation is true, we can say that any value of x that satisfies is always bigger than k, right? Because x is equal to k plus something positive. So we can say x is always greater than equal to k, right? I hope you understand this step. X is always greater than k. Why? Because now we will get a upper bound for k, right? K is less than equal to x. So the lowest possible value of x is the upper bound of k, right? And what is the lowest possible value of x here? The value of x here would be one of the two roots satisfying this equation, right? One of the two roots satisfying this equation, and let's take the lower possible root. The lower possible root will be 2k plus 1. Lower possible root for this equation will be 2k plus 1 minus root over this discriminant, which is coming out to be 4k plus 9 by 2. And that root is actually greater than equal to k, right? This root should be greater than equal to k. Why are we saying this? Because this root satisfies this equation, and for any value of x satisfying this equation, x is always greater than equal to k. So that gives us an upper bound for k, right? Here what we have is a lower bound for k. K is greater than minus 9 by 4, and this will give us an upper bound for k. Because if you simplify this a little bit, you'll get 2k plus 1 minus root over 4k plus 9 is greater than equal to 2k. 2k gets cancelled. You get 1 is greater than 4k plus 9, and you'll get minus 8 is greater than 4k. So k is less than minus 2, right? Less than equal to minus 2. So basically, we are getting k is less than equal to minus 2 from here, and k is greater than minus 9 by 4 from here. And we get the interval for k, basically, minus 9 by 4 to minus 2. This is the range that k exists in. How did we solve this problem? We first realized that the equation, the function is a monotonically increasing function. So its values will increase from when we put a in it to when we put b in it. And that range must be equal to a and b. And because that must be equal to a and b, we got that a and b are the roots of this quadratic after simplifying a little bit. So the first condition is obviously the discriminant condition, which means the discriminant is positive, which gives us one bound for k. The other condition is to realize, is obtained by realizing that the k values will be less than equal to x. And if k values are less than equal to x, where x is one of the roots, let's take the lower root, which will give us a more stricter condition on k. And from there, we get 1 k is less than equal to minus 2. So that gives us the overall range of the k variables, right? Let's move on. Question 4. This says, suppose f of x is equal to x square plus ax plus b cos x. And we are given that x is such that f of x equal to 0, x belongs to R. This set is equal to x is such that f of x equal to 0, x belongs to R, and both the sets are not equal to the null set. We have to find all possible values of A and B. So we have seen some questions like this before in the previous section. We saw a question about stable points and fixed stable points. So this reminds us of that. So let's try it in a similar manner. So we'll say suppose x naught belongs to the first set, belongs to this set. X is such that f of x equal to 0, x belongs to R, right? Suppose x naught belongs to this set. That means that f of x naught is equal to 0. Now, you will realize that if f of x naught is 0, since x naught belongs to this set and the two sets are equal, let's call it set A and let's call this set B. X naught belongs to A implies that x naught also belongs to B, right? So if x naught belongs to A, we know that f of x naught is 0. And if x naught belongs to B, we know that f of x naught should also be 0, which means that f of x naught is 0, f of 0 is 0. So from here, we get f of 0 is 0 means B is 0. Because if you put 0 in this function, you will get f of 0 is equal to B. B is 0. So what we have just now gotten is we have obtained the value of B. How did we get it? We said that if any element belongs to the first set, it will also belong to the second set because the two sets are equal. And from the first set, we get f of x naught is 0. And if you put it in the second set condition, you get f of 0 is 0, which implies B is 0, right? So I hope everyone has gotten this argument. Now what we will say is we'll calculate the value of f of x. So since B is 0, f of x is basically x squared plus ax or x into x plus a, right? So f of x is this. So what is set A here? Set A can be basically 0 and minus a, right? Set A can be 0 and minus a because set A is the set of values of x for which f of x is 0, right? So if set A is 0 and minus a, that means set B also must be 0 and minus a, right? And set B cannot have any other extra elements, right? So now let's look at f of x. F of x becomes basically f of x into f of x plus a, which becomes x into x plus a, and inside you can multiply and get x squared plus ax plus a, right? Now, if we want to find the set of elements of set B, we have to say f of x is equal to 0. All those satisfying this equation will be elements of set B, right? So this equation is clearly satisfied for x is equal to 0 and minus a. Those are clearly roots of this, right? But you could also have roots here, right? If you have some roots here, we can see 0 and minus a are not roots of this equation. 0 and minus a are not roots here. Roots here. Unless, of course, a is 0. If a is 0, then the equation is simple. F of x becomes simply x squared, right? A could be 0. That is possibility. A 0 satisfies all the conditions. But if a is not 0, then 0 and minus no a are not roots here. So that means that f of x equal to 0 will have other roots beyond 0 and minus a if this quadratic has a solution, right? If this quadratic has some roots which are not 0 and minus a, that means set B will have some extra elements, but set A had only these two elements, right? So how will we ensure that the two sets are equal? The only condition that we can say is that this quadratic has no roots. And this quadratic has no roots if the discriminant is less than 0 So which means a square minus 4a is less than 0, which means basically 0 is less than a is less than 4. And we have seen already that a is equal to 0 satisfies the condition in the problem that both the systems have the same roots. If a is equal to 0, function is simply x square, and the only element in both the sets is 0, right? So we will say that 0 is possible here, 4 is not possible, and a belongs to basically 0 to 4, and b is equal to 0. These are the possible values of the two variables. I hope you have understood what we are doing. We are just making a logical argument that says that both the sets have to have the same elements. So f of x, the equation is becoming a fourth degree equation. We need to ensure that it only has roots 0 and minus a. It cannot have any other real roots, because then set A will not be equal to set B, right? So in order to do that, we put the condition discriminant less than 0 for this quadratic, and we get 0 to 4. So basically then we find out the range of A and B. A ranges from 0 included to 4 not included, whereas B is always equal to 0, right? I hope you have understood the solution here. Let's move on to the next one. This is question 5. The question says that let f of x be equal to x power 5 plus ax cube plus bx plus c cube root of x plus 8, where a, b, and c belong to real numbers, right? Now we are given that f of minus 2 is equal to 10, and we are being asked to find the value of f of 2. Okay, so since they have given us only one value of the function, it is impossible from there to find three constants a, b, and c, right? If with one equation we cannot find a, b, and c, and they are asking us for another value of the function, so we have to use some properties of the function, which will basically, some information must be hidden in the function, which will help us solve this, right? So let's think about it. You can quickly see here that f of x minus 8 is equal to x power 5 plus ax cube plus bx plus c cube root of x. And this whole function on the right hand side has odd powers and basically is an odd function. Can you see that? If you put minus x in the right hand side, it becomes minus x power 5 minus ax cube minus bx and minus c cube root of x. So this is an odd function. So we can say that let's call gx is equal to f of x minus 8, and we have therefore gx is odd. If gx is odd, we know that g of minus x is equal to minus of g of x. So g of minus x would be f of minus x minus 8 is equal to minus of f of x minus 8. So we'll get f of x plus f of minus x is equal to 16. We should be able to deduce this condition because of the fact that g of x is an odd function. And now that we have this nice condition, we can easily find the relationship here, because f of 2 plus f of minus 2 will be equal to 16. And since f of minus 2 is given as 10, f of 2 must be 6. Right? So the main idea in the problem is to recognize that normal process of putting the values will not get us anywhere, because we don't have enough information. We just have one data point. It doesn't give us the values of three different parameters. So we have to look at the nature of the function, look at the structure of the terms, and figure out that it's an odd function. If we do that, the question is pretty obvious, right? Okay, let's move on to the next one. This question says, let x and y be real numbers such that x minus 1 whole cube plus 2018 x minus 1 equal to minus 1, and y minus 1 whole cube plus 2018 y minus 1 is equal to 1, right? We have to find the value of x plus y. Find x plus y. Okay, so here again, this looks like a cubic. If you simply add it, it will become 0, but then you will be stuck. You will not be able to simplify it after that point. So you can try that algebraic manipulation, but what I would suggest is slightly different. We can say that if I put a -1 here, I get minus of y minus 1 whole cube minus of 2018 y minus 1 is equal to -1. And I can write this as 1 minus y whole cube plus 2018 1 minus y is equal to -1. And I also have x minus 1 whole cube plus 2018 x minus 1 is equal to -1. So these are my two equations. I have just changed the equations a little bit. And now I have two equations, one involving x, one involving y. Both are equal to -1. Right? And the nature of the equations is also same. So that suggests that we can try and think of a function f of t, which is t cube plus 2018 t, right? Can you see that both the equations satisfy the same structure? So we can think of a single function f, which is t cube plus 2018 t, and we can say that f dash t is equal to 3t square plus 2018. So we know that it's an increasing function. Increasing function because f dash t is always positive. The derivative is always positive. So f of t is increasing function. And if f of t is increasing function, what is the meaning of increasing function? F of x1 is equal to f of x2 will happen only if x1 is equal to x2, right? For any monotonically increasing or decreasing function, the value of the function cannot be equal at 2 points whose inputs are different, right? If f of x1 is equal to f of x2, that means x1 must be equal to x2. The function is not ever going to have the same value once it goes away from x1, right? So here we can see that f of 1 minus y is equal to f of x minus 1, right? From these equations and the function definition of f of x, we can conclude that f of 1 minus y is -1 and f of x minus 1 is -1. So that means f of 1 minus y is equal to f of x minus 1. And that means 1 minus y is equal to x minus 1, right? Because the function f was purely increasing. This result is not true for other types of functions which may decrease or increase or which may have maxima or minima points. It is only true for strictly increasing or strictly decreasing functions. So we must have 1 minus y is equal to x minus 1, which implies x plus y is equal to 2. Right? From this equation, it is obvious that x plus y value is equal to 2. So that is a very interesting application of our monotonicity of functions. You would not have guessed that we will be using function properties here. The standard method here would be to try to manipulate it using algebra techniques and using some identities. But obviously, this is much faster. So hopefully, you have learned something from this. The next one is this. Let f of x be defined on R such that for every real number x, we have f of x plus 3 multiplied by f of x minus 4 is equal to -1. Also, suppose for x belongs to 0 to 7, f of x is defined as f of x is equal to log base 2 9 minus x. We have to find the value of f of -100. So we have to find the value of f of -100 in this equation, in this function. However, they have not defined f of x for x belongs to anything beyond 0 to 7. f of x definition has been given only for x belongs to 0 to 7. And that definition involves this log of base 2 9 minus x, right? Now, the condition that they have given, which is true for all real x, is this condition. F of x plus 3 and f of x minus 4 product is equal to minus 1, right? So we have to basically somehow guess or find out what f of minus 100 will be when we don't know how the function is defined in that region, right? So that is a little bit of a tricky one, because what we'll have to do here is to guess how the function will behave in regions where we don't even know its definition, right? So let's think of what we can do with this result. So if f of x plus 3 and f of x minus 4 is minus 1, f of x plus 3 multiplied by f of x minus 4 is minus 1. If I put, instead of x, if I put x plus 4 here, what I will get is f of x plus 4 plus 3, so x plus 7, multiplied by f of x plus 4 minus 4, so f of x is equal to minus 1, right? So that implies f of x is equal to minus 1 by f of x plus 7, right? And if instead of, this is the first step basically, and then the second step, what we'll do is we'll try to get f of x plus 7 in a different way. We will say instead of x, we will put x plus 11, right? So this will become x plus 11 plus 3. So x plus 14 multiplied by, if you put x plus 11 here, you will get f of x plus 7 is equal to minus 1, right? And that implies that f of x plus 14 is equal to minus 1 by f of x plus 7 again, right? Why did I do x plus 11? Because I wanted to get f of x plus 7 again. So from here, we can easily see that f of x is equal to f of x plus 14, right? From these two results, we have been able to see that f of x is equal to f of x plus 14. So f of x has a periodicity of 14, right? Period of 14. So that means if I know my values from 0 to 7, I should be able to technically find the values for any other value. So we can say f of minus 100 will be the same as f of minus 100 plus 7 into 14, right? Because 14 is the period, minus 100 plus 14 would be same value. Minus 100 plus twice of 14 will also be the same value. So this will become basically f of minus 2, right? And f of minus 2, we can say, putting x is equal to 2 in this equation, we will get f of 5 into f of minus 2 is equal to minus 1. So that implies that f of minus 2 is equal to minus 1 by f of 5, right? And minus 1 by f of 5 is properly defined in this region, right? If x was between 0 to 7, we know the definition. So we'll say it is minus 1 by f of 5, which is log 2. 9 minus 5 is 4. So the answer is simply minus 1 by 2, right? This is minus 1 by log 2, 4, right? So f of minus 100 is coming out to be minus half. How did we get this? We got this because we realized that this condition can be used and we can prove that f of x is equal to f of x plus 14. And 14 is the period of the f of x, right? How did I prove this? In the first step here, we put instead of x, we put x plus 4. And in the second step, we said instead of x, put x plus 11. Why did we choose these two numbers? We chose x plus 4 because we wanted to get fx, right? And once we did that, we realized that fx is linked to f of x plus 7, right? So next time that I was choosing, I needed something that has f of x plus 7. How do I get f of x plus 7 again? Instead of here, I try to get it here by putting x plus 11 here. So I got f of x plus 14 into f of x plus 7 is equal to minus 1. And basically, you can even divide the two equations here and you will get f of x by f of x plus 14 is equal to 1, right? So hopefully you understood how we defined the period, found the period of the function. Once we can find the period, we can find any values of the function because we know all the values between 0 to 7, right? After that, you keep adding 14 or subtracting 14 and you will end up having the same values, right? So that ends this question. The next one is this one. A and B are solutions to the equations log 2x plus x minus 3 equal to 0 and 2 power x plus x minus 3 is equal to 0 respectively. Okay, and we have to find a plus b, and we also have to find log 2a plus 2 power b. So we have been told that a is the solution of this equation and b is the solution of this equation, right? And we have to somehow find the values of a plus b and this, right? So let's think about it here. Both the equations can be written like this: log 2x is equal to 3 minus x and 2 power x is equal to 3 minus x. And you should realize that 2 power x and log 2x are inverse of each other. These are inverse functions. So if you want to draw a graph here, log 2x will be somewhat like this, and 2 power x will be the reflection of that on y is equal to x line. This line is y is equal to x. This graph is y is equal to 2 power x. From here 1, and this is also 1. This is 1 comma 0, this is 0 comma 1, right? And this graph is y is equal to log base 2x, right? And if I also draw the graph of 3 minus x, you will realize that y is equal to 3 minus x is a straight line graph, and that straight line is perpendicular to the y is equal to x line, right? These two lines are perpendicular. And since we know that the graphs are mirror images of each other about y is equal to x, so this line, this perpendicular line basically says that this point and this point are reflections of each other, right? Point A and point B are reflections of each other on the mirror of y is equal to x, right? Great. So if you realize that, then we'll be able to quickly solve this. Let's call this middle point as M. This M point is the intersection point of the graphs of y is equal to x and y is equal to 3 minus x. And if you solve x is equal to 3 minus x, you'll get x is equal to 3 by 2. So this middle point is basically 3 by 2 comma 3 by 2, right? And this point A is the intersection of 3 minus x with 2 power x. So I have labeled it incorrectly. So let's label this as B and this as A. And 3 minus x and 2 power x is the solution of this equation where x was equal to B according to the problem. So this point is B comma 2 power B. And what is this point? This point is A comma log 2A, right? So this is the solution of the first equation, point A, and this is the solution of the second equation, point B. And both the points are basically reflections of each other on the y is equal to x line, which is the mirror line, which is how two inverse functions behave, right? So from here we can easily see that M is midpoint of AB. M is the midpoint of AB line segment. Therefore, A plus B by 2 will be the x coordinate of M, which is 3 by 2. So which implies A plus B is equal to 3. And also the y coordinates 2 power B plus log base 2A by 2 is also equal to 3 by 2. So this is also equal to 3. So both the answers here are 3, and the answers come by simple graphs. You have to realize that log 2x and 2 power x are mirror images of each other about the y is equal to x line. And you have to realize also that 3 minus x, the line, is perpendicular to y is equal to x. And therefore, it will be like a proper mirror image reflection of each other. If it was not perpendicular, we could not have said this. If the line was like this, random line, we could not have said this plus this by 2 is this, right? Because it is perpendicular, this is going to be equal to this because it's a direct reflection, right? I hope you understood what we are doing in this solution. Let's move on to the next one. This question, we say that let f of x be defined, be a function defined on R such that f of 0 is 2008. Suppose f of x plus 2 minus f of x is less than equal to 3 into 2 power x, and f of x plus 6 minus f of x is greater than equal to 63 into 2 power x. We are given these two conditions. Find f of 2008. We are supposed to find f of 2008, right? Okay. Now, there are these two conditions. We have to use these conditions somehow. Okay, so let's think about f of x plus 2 minus f of x, right? Now, we have been given this inequality, right? Can we use this inequality together with this inequality somehow? That is what I want to do. So, if I say f of x plus 2 minus f of x, I can write it as f of x plus 2 minus f of x plus 4. And then I need a plus f of x plus 4 and minus f of x plus 6. And then a plus f of x plus 6 and a minus of f of x. I'm basically writing all the terms that are missing. F of x plus 2, f of x plus 4, f of x plus 6, and f of x. And I have done minus plus here and minus plus here in order to ensure that my overall inequality is not changed. F of x plus 2 minus f of x is still the same. Now I can write this as negative of f of x plus 4 minus f of x plus 2. And the second term also with a negative sign, negative of f of x plus 6 minus f of x plus 4. And the last one with a positive sign, f of x plus 6 minus f of x, right? Okay. Now, what is the benefit? Think of this inequality. We have f of x plus 2 minus f of x is less than equal to 3 into 2 power x. So if I do f of x plus 4 minus f of x minus f of x plus 2, that will be less than equal to 3 into 2 power x plus 2, right? So if I put a minus sign, minus of this will be greater than equal to minus of 3 into 2 power x plus 2, right? So I can say this first term will be greater than minus 3 into 2 power x plus 2, right? Similarly, the second term, doing the same steps here, except now here instead of x plus 4, I put x plus 6 and x plus 4. So we'll have x plus 4 here, right? Exactly same steps. And I will say this is greater than equal to minus of 3 into 2 power x plus 4, right? And we already know that this is greater than equal to this. So this is greater than equal to plus 63 into 2 power x, right? Each of these terms I'm saying is greater than equal to this is greater than equal to this, and this is greater than equal to this. How did I get this? I got this by doing this and then multiplying by minus 1 to reverse the sign. It was less than equal to inequality. I multiplied by minus 1 to reverse the sign, right? So this becomes greater than equal to basically 2 power 2 is 4. So minus 12 into 2 power x. And this is 16 minus 48 into 2 power x plus 63 into 2 power x. So basically that is equal to 3 into 2 power x, right? So what I'm getting now is a nice result. I'm getting that f of x plus 2 minus f of x is greater than equal to 3 into 2 power x. And we already know that it is less than equal to also 3 into 2 power x. So how can something be less than equal to and greater than equal to the same value? The only possibility is that it is equal to 3 into 2 power x, right? So basically now this implies for us that f of x plus 2 minus f of x is equal to 3 into 2 power x, right? Now, if we have this, we should be able to basically find the series. We have to find f of 2008. So we will keep using that. F of 2008 will be equal to f of 2008 minus f of 2006 plus f of 2006 minus f of 2004, right? And so on, plus f of 2 minus f of 0, and finally a plus f of 0, right? Okay, so each of these brackets, we can use this result. We can say this is 3 into 2 power 2006 plus 2 power 2004 plus so on till 2 square plus 2 power 0 for this term. And we have a plus f of 0, right? Okay, so this is a straightforward GP. It has 1004 terms. So this becomes 3 into 4 to the power 1004 minus 1 by 4 minus 1, right? Correct. The common ratio is 2 square or 4. 4 is the common ratio. And first term is, you can say, is 1, right? First term is 1. So that this is the sum of the GP plus f of 0, right? This becomes equal to 3 cancels here, and it becomes basically 4 to the power 1004 minus 1 plus f of 0, which is now, what was f of 0? I think f of 0 was given, f of 0 was given to us as 2008. So it is 4 to the power 1004 minus 1 plus 2008, which is becoming 2007 plus 2 to the power 2008. That becomes our answer. F of 2008 is coming by using this result repeatedly. And we get a GP sum at the end, right? How did we get this result? We got this result by realizing that the two inequalities can be used in order to prove that f of x plus 2 minus f of x is greater than equal to 3 into 2 power x also, right? If you get that, you'll be basically be able to say that since we have greater than equal to and less than equal to, that means that it must be equal to 3 into 2 power x. Okay, let's go to the next one. We have to solve this inequality. Solve the inequality log base 2 x power 12 plus 3x power 10 plus 5x power 8 plus 3x power 6 plus 1 less than 1 plus log base 2 x power 4 plus 1, right? First step would be to simplify this a little bit. This can be written as log base 2. This will become 2x power 4 plus 2. And we have this equation, right? Since log is an increasing function, we can write this as, we can remove the log and write it simply as this is less than that, right? We can rewrite this inequality like this: x power 12 plus 3x power 10 plus 5x power 8 plus 3x power 6 plus 1 is less than 2x power 4 plus 2. At this stage, we can say that if x is 0, this inequality is satisfied because 1 is less than 2. So now x is 0 is a solution for this inequality. And now we will say that assume x is not equal to 0. So if we can assume that, then we will be able to divide by powers of x, right? What I want to use here is I want to divide by x power 6 on both sides. So if I do that, I'll get x power 6 plus 3x power 4 plus 5x squared plus 3 plus 1 by x power 6 is less than 2 by x squared plus 2 by x power 6, right? So this becomes basically 2 by x square plus 1 by x power 6, cancelling one of these terms, is greater than x power 6 plus 3x power 4 plus 5x square. But 5x square I can write as 3x square plus 1, and then we have 2x square left over plus 2, right? So I have gotten this inequality right now. I have also realized that x is equal to 0 solves the inequality. It is a solution. Now I'll simplify this a little more. So I'm just rubbing off this part here on top for some space, and let's work it out. So we have here 2 by x square plus 1 by x power 6 is greater than x power 6 plus 3x power 4 plus 3x square plus 1 plus 2 times x square plus 1. And we can see here this is x square plus 1 whole cube plus 2 times x square plus 1. And what is this here? It is 2 into 1 by x square plus 1 by x square whole cube is greater than this, right? So can you see that both sides have the same nature of the function? We can take a new function g of t, which is equal to t cube plus 2t, right? And this side is basically g of 1 by x square. And this side is basically g of x square plus 1, right? Can you see that this function fits both the conditions? G of 1 by x square is this, g of x square plus 1 is this, and you can easily see here g dash t is equal to 3t square plus 2. So g is an increasing function. G is an increasing function. Therefore, g of 1 by x square is greater than g of x square plus 1, implies 1 by x square is greater than x square plus 1, right? 1 by x square is greater than 1 by x square plus 1 because g is increasing and one side g of 1 by x square is greater than g of x square plus 1, right? So that easily solves the inequality for us. Now we get a quadratic. 1 by x square is greater than x square plus 1. That means basically that x power 4 plus x square minus 1 is less than 0. This will happen only when x square is between the two roots. X square is between minus 1 minus root 5 by 2 to minus 1 plus root 5 by 2. If x square lies in this range, since this is obviously negative, x square basically lies between 0 to minus 1 plus root 5 by 2, which implies that x will lie between minus 1 plus root 5 by 2 root of that to minus 1 plus root 5 by negative root of this. And this is the positive root, right? So this is my solution, which comes directly from here. This is a quadratic. The solution of this quadratic is, it's an upward facing parabola. So x square has to lie between the two roots of the quadratic, right? For it to be negative. And once you get this is negative. So x square will always be positive. So x square has to be less than this. So that implies this, right? So we have solved this inequality again in an unusual way. We have not done direct algebra. We use the properties of function. We defined a new function g of t is equal to t cube plus 2t. And we saw that the g function was increasing. And both sides were written in terms of g only, right? Okay. Let's go on to the next one. We have been given if mod of 2 power x minus a is less than mod of 5 minus 2 power x holds for all x belonging to 1 to 2, right? We have to find the range of A. Find the range of A. So first of all, both sides have 2 power x involved. So let's call t is equal to 2 power x. And if x belongs to 1 to 2, it implies that t will belong to 2 to 4, right? t belongs to 2 to 4. And the inequality starts becoming like this: t minus a mod is less than 5 minus t, right? For all t belongs to 2 to 4, right? Okay. Now, if t belongs to 2 to 4, and we have this inequality, then obviously square of this should be less than this. So t minus a whole square is less than 5 minus t whole square. If you simply bring it to one side and simplify, you will get this: 2t minus a minus 5 into 5 minus a is less than 0, right? How did I get this? I got this by just doing a square minus b square and applying this identity, right? Now think of this equation. This is 2t 5 minus a plus 5 into 5 minus a is less than 0, right? Now, for a given a, for a given constant a, for a given constant a, can you see that this is a linear function? F of t is equal to 2t minus a minus 5 into 5 minus a is a linear function on t, function of t, right? So linear function because t comes only with 1 degree power, right? It's a straight line in t, right? Great. So if I need to ensure that f of t is less than 0, right? For all t belongs to 2 to 4, how can I ensure that a linear function is always less than 0 for all t belonging to 2 to 4? I just have to say that f of 2 should be less than 0 and f of 4 should be less than 0. The two endpoints of the linear function should be less than 0 if I want to make sure that the linear function is always less than 0 in that whole interval, right? So keep this logic in mind. A linear function is monotonic and increasing or decreasing. So if you want to ensure that it is always less than a particular value, you need to check the endpoints. And if the endpoints are less than that value, then the linear function is also less than that value, right? So now we can just do f of 2 is less than 0 and f of 4 is less than 0, which becomes very easy because our f of t was what? 2t minus a minus 5 multiplied by 5 minus a. And f of 2 basically is minus 1 minus a multiplied by 5 minus a must be less than 0. And also f of 4 is equal to 3 minus a multiplied by 5 minus a. And this also must be less than 0. We can solve both of these together by wavy curve method. Wavy curve method and find the range of a. And if you solve it yourself, you'll realize that a belongs to the set 3 to 5. And that is the solution of this inequality. How did we get this? Remember, we had 2 power x in the beginning. We changed the variable. We got t is equal to 2 power x, and that is our new parameter. And our t varies from 2 to 4. And after that, on simplifying the inequality, we realized that the inequality was like a linear function of t. And we needed to make sure that it was less than 0 throughout. So if it's a linear function, we can just check the endpoints, right? And that's it. That's how we solved it. Let's move on to the next one. In this question, we say let x and y and z belongs to 0 to 1. And we have to find the maximum value. Find the maximum value of m, which is equal to root over mod of x minus y plus root over mod of y minus z plus root over mod of z minus x. We have to find the maximum value of this where x, y, z is belonging to 0 to 1, right? Obviously, I don't want to use calculus. I'll be using methods of functions that we are aware of and some basic inequalities. We have x, y, z belonging to 1. So without loss of generality, we can assume that 0 is less than equal to x, less than equal to y, less than equal to z, less than equal to 1, right? This is, we can assume any order. I have just assumed one particular order. So there, without loss of generality, I can write this, and then the inequality becomes m is equal to root over y minus x plus root over z minus y plus root over z minus x. I have removed the modulus sign because I know now the order of x, y, z, right? Okay. So now let's think of root over y minus x plus root over z minus y, right? I need some inequalities. So let's think of trying to get the inequality on these two terms, right? So I can write this as 1 into root over y minus x plus 1 into root over z minus y. And by Cauchy's inequality, this is like a dot product of two terms. So it should be less than equal to root over 1 square plus 1 square multiplied by y minus x plus z minus y, right? Well, what am I doing here? I am saying that a dot b is less than equal to mod a into mod b, right? Cauchy's inequality basically, or you can write it as summation of ai bi is less than equal to root over summation of a square multiplied by summation of b square, right? Correct. So this is Cauchy-Schwarz inequality, and that implies that root over 1 minus x plus root over z minus y is less than equal to root over 2, and this is y gets cancelled and this is z minus x, right? Great. So when now we have to look at m, we can write m as what? M can be written as less than equal to root 2 root over z minus x plus root over z minus x. M is less than equal to root 2 plus 1 root over z minus x. How did I get that? M was basically root over y minus x plus root over z minus y plus root over z minus x. And we have already established that root over y minus x plus root over z minus y is less than equal to root over 2 times z minus x, right? So m is less than equal to root 2 plus 1 root over z minus x. Now, what is the maximum value of this? Maximum value of this is 1, right? Because z can be 1, x can be 0, and y can be half, right? If y is half, this is equal to this is equal to half. Both are half half, which is equal to root over 2 times 1, right? Correct. So the maximum value of this is 1, and we are getting m is less than equal to root 2 plus 1, right? I just need to check whether this equality can happen or not. So equality should happen in this equality should happen when y minus x is equal to z minus y, which means, yeah, which means 2y is equal to x plus z. And this is 0, this is 1, then y is half, right? At 0, 1 and half, I think you get the value of root 2 plus 1, right? So basically we have to use Cauchy-Schwarz here. The maximum value is coming out to be root 2 plus 1, and that's the solution for this one. Let's look at another one. Find the maximum and minimum values. Find the maximum and minimum values of f of x is equal to root over 8x minus x squared minus root over 14x minus x squared minus 48, right? So first thing that we will do here is look at the domain of this function. Domain will be the intersection of 8x minus x squared greater than equal to 0, and also 14x minus x squared minus 48 is greater than equal to 0. You can solve this yourself and you will get that x belongs to 6 to 8. Because this can be factorized as x minus 6, 6 minus 8 minus x and all. So we can rewrite this function f of x as root over 8 minus x common, and inside you have root of x minus root over x minus 6. And if we rationalize this function a little bit, you will get x minus 6 by root over x plus root over x minus 6. What am I doing here? I'm multiplying up and down by root over x plus root over x minus 6. I'm rationalizing the function. So this becomes 6 times root over 8 minus 6 by root over x plus root over x minus 6. Right? Okay. Why am I writing this function like this? Because if I write this function like this, it is obvious to figure out the maxima minima of this function without doing calculus. I'm showing you a method which does not involve calculus. Calculus methods are available, but it will be a little long. It will be longer than what we'll do here, right? So think about it. The function is defined only from x goes from 6 to 8. And in 6 to 8, x belongs to 6 to 8. We can easily see that root over 8 minus x decreases. The value of root over 8 minus x decreases, and root over x plus root over x minus 6 increases. As you put the values of x from 6 to 8, the value of the denominator always increases and the value of the numerator always decreases. So overall, fx is a decreasing function. Fx is a decreasing function on 6 to 8. Right? That is obvious from the nature of the expression we have gotten for fx, and therefore f max will happen at f of 6, since it is a decreasing function, and f of 6 is equal to 2 root 3, and f min will happen at f of 8, and that is equal to 0. So basically we end up getting that the maximum value of the function is 2 root 3 and the minimum is 0. We just did that by realizing the nature of the function, and it's a decreasing function on the domain, right? So if it is an increasing or decreasing function, purely monotonically increasing or decreasing, the only points we have to check are the endpoints for that function, right? Let's look at the last and final problem for this section of the syllabus. This is question number 14. Let x and y be non-negative real numbers such that we have root over 1 minus x square by 4 plus root over 1 minus y square by 16 is equal to 3 by 2. We have to find the maximum value of xy. Okay. So here we will use two standard identities. The first identity is basically a square plus b square, or rather we'll say a plus b whole square is always less than equal to 2 times a square plus b square. Why? We can easily show this, because if you take it to the other side, 0 is less than equal to 2 times a square plus b square minus a plus b whole square. And if you simplify this, you'll get a square plus b square minus 2ab. And 0 is clearly less than a minus b whole square, right? So why am I going to use this identity here? Because I want to remove the roots here, right? So I can say that root over 1 minus x square by 4 plus root over 1 minus y square by 16 whole square is less than equal to twice of a square is 1 minus x square by 4 plus b square is 1 minus y square by 16, right? Now this is equal to 3 by 2 is given in the problem. So we get 9 by 4 is less than equal to twice of 2 minus x square by 4 minus y square by 16, right? So this is 9 by 8. So you bring everything to one side, all the variables, you will get this is less than equal to 4 minus 9 by 4, or 2 minus 9 by 8, which becomes 7 by 8. And this becomes 4x square plus y square is less than equal to 14. So after a little bit of simplification and using this identity, we are getting 4x square plus y square is less than equal to 14, right? Now, the second identity that I want to use is basically saying that what can I say about 4x square plus y square? 4x square plus y square. And if you use AMGM identity by 2, the AM of these two numbers is always greater than equal to root over 4x square into y square, which is the GM of these two numbers. So we get 4x square plus y square is greater than equal to 2 goes on this side and becomes 4xy, right? Correct? So 4x square plus y square is greater than equal to 4xy, and we have 14 is greater than equal to this. So we have basically 4xy less than equal to 14. So that means xy is less than equal to 7 by 2. 14 by 4 or xy is less than equal to 7 by 2. So what are we doing here? We are saying we are using AMGM and a standard a square plus b square whole a plus b whole square is less than 2 times a square plus b square identity. And we are getting the maximum value of this is less than 7 by 2. So that's a nice trick here that helps you analyze the maximum and minima of a multivariable expression without doing any calculus. We can do this by several other methods. We can do parameterizations in terms of trigonometry also, but this is the fastest way to get it, right? So I hope you have learned something from this video. This video was basically a collection of problems aimed to help you analyze functions, graphs, monotonicity, maxima, minima, and covering a lot of topics. We are doing this section of the syllabus quite quickly because we'll get into details of inequalities starting from the next section. And then we'll go slowly and we'll go over all the types of inequalities and all. So see you in the next video.